Hi, in this video, we'll be continuing our study of cardinality. We have defined previously when two sets are the same in size. We have also defined what is a finite set and an infinite set. And now we want to have some properties when we count objects that we want to hold true in the most basic form in sizes in cardinality. So if you remember our video on counting, if you can go rewatch it, you have learned certain principles in counting. The first is the addition principle. And so we want to say this is true and is consistent with our intuition. But intuition is not the proof, and so we need to prove this to be true and based on our definition. So what does it mean for A union B, this set, to have a cardinality that is equal to the cardinality of A plus the cardinality of B? Well, if A equals to n, that means there's a bijection with the n reference set. And if B is equals to m, then there's a bijection with the m reference set. And so when A plus B is equals to n plus m. And hence, we just need this set to have a cardinality of n plus m. That means there's a bijection with n plus m reference set. Now, how do we want to form this bijection? The hardest part about proving things about cardinality is always to create the bijection. And so we need to carefully create it, but in this case, it is fairly simple because if we list out the first n elements, we can just put them into A. And then if we have the n plus 1 elements to m plus m elements, we can put them into B. And because of our assumption that A intersect B is disjoint, none of these elements over here will cross over also. And none of them will put into the same input. Hence, we can just define our function h by being f from 1 to n and g from n plus 1 to m plus n. And now h is well defined because A intersect B is empty. And it's also a bijection, which you can check. I'll leave it to you, but it should be fairly simple and obvious because f is a bijection and g is a bijection. Next, we also have the multiplication principle, but this time the bijection is a little harder to define. So the multiplication principle states that A cross B is the size of cardinality of A multiplied with the cardinality of B. So it's just nm. So it means we need to find a bijection with A cross B to nm. So the function that I've defined makes use of the division algorithm. And I'll explain to you how people come out of this. So for any of the input, the output will be gy minus 1 times n plus fx. The reason for this is gy times n ranges from 1 to mn. Then now you minus away n from both sides. And so you need to add back the n part, which is fx. So at the end of the day, this will still be in the range of nm from 1 to nm. And hence, this is well defined. And by the uniqueness of the division algorithm, you know this and this are unique. And so this gives us an easy proof of why this will be a bijection. Of course, this is only one of the bijection that you can come up with, and there could be multiple bijections. But the reason why we come up with this is we want to relate NM to some function of G and some function of F. And so the natural thing to do is just to take like of M, like M, multiplied the thinking is M equals to QM plus R. And so you want to make use of this idea to help you get NM over here. You can read online for different type of bijections if you don't think this is the most obvious to you. But you can also relook at the proof and prove that it's actually a bijection and the well-definedness is true to better understand this function. And so that is the multiplication principle and the addition principle that we've just proven or thought through. The last one will be the subset principle. And this will be an important principle, and I will explain why later on. So if A is a subset of B and B is finite, then A is finite and cardinality of A will be less than the cardinality of B. If you recall, this actually builds on the idea of the pigeonhole principle that we have stated earlier. But now instead of just being a proper subset, it can equal. And so you can't say that A is... We know that A is not equinumerous to B. But now this proposition proves to us why A must be strictly less than or equals to B. And so we can do induction on B, where B is n. If n is 0, means B is empty, A is empty, and so A cardinality is 0, B is strictly less than A is strictly less than B, inequality holds. So now we assume that the case of M holds. If the cardinality of B is M, then A is less than or equals to M. And now, for the case of M plus 1, there exists a bijection from M plus 1 to B. And so B can be listed out in the following from 1 to M plus 1. And if A is a subset of B, there are two cases. Either B M plus 1 is an element of A, and so A being a subset of B, not an element of A, that means A must be a subset of B to B1 to Bm. And by the induction hypothesis, this means A is finite and A will be less than or equals to M, which is less than B. So it is true. In case 2, Bm plus 1 must be an element of A, and so X equals to A minus away this Bm plus 1 must be a subset of B1 to Bm, because A is a subset of B1 to Bm plus 1. Now, you take away this, it must be of course within 1 to M. By the induction hypothesis, this means X is finite, X is less than or equals to M. You add back the Bm plus 1 to get A. Now it must be less than or equals to Bm plus 1, which is B cardinality. And hence, you have proven this proposition using induction. And so, a corollary of it is now that because you know if B is finite, A will be finite. If you take the contrapositive, if A is infinite, then B is infinite. And so you know that N is infinite. Z, Q, and R all containing N will make it infinite as well. And so now you have you can prove easier more things about which sets are infinite by using this criterion, if you will. And so you just need to find a subset that is infinite, and then you have proven that the whole set is infinite. And so this gives us a criterion for finite and infiniteness, and we can use it to prove when two sets are infinite. In the next video, I'll be going through when two sets are countable, and you'll see how the criterion for countability is similar. Catch you in the next one. Thank you for listening, and I hope you've liked it. Feel free to like, share, and subscribe.